This talk describes a topological representation of signals based on factoring smooth functions. It's primarily intended to talk about sonar signals, but other signals would work just fine too. This is joint work with a number of students of mine and funded by the Office of Naval Research. If you're interested in further details about the mathematics that I'm presenting, there is an archive paper that you can read that goes into considerably more detail. This talk is about sonar signatures, and in particular circular synthetic aperture sonar signatures. These are data that are collected about a target in a scene in which the sensor orbits the target on a circular path. As the sensor moves around the target, it sends out pulses and it records the echoes. The echoes are effectively a function of two variables: the look angle, so the angle that the sensor makes with some arbitrary direction as it moves around the target, and the frequency. So the echoes get recorded. You can imagine them coming in time, or you can imagine them coming in frequency. Now, traditionally, what people do with this kind of data is they form the data into an image, which looks nice and focused when you're all done, provided you have a good control of the sensor trajectory and good control of the environment. So for instance, if you look at the target on the left, sort of schematically, there are three bright spots, and in the image they show up as three bright spots focused on the image on the right. Now, the problem with this is that this can be very difficult to get a good focused image if the sensor parameters are not well known, the sensor moves, or the environment is not quite what you expected. Well, what can you do in that case? Well, you can still use the raw data and still identify the kind of target. The typical kind of target that you might want to understand, well, it probably comes from a dictionary, and so you may in fact have several different data sets and you want to know which target is which. Well, what this means is you have some kind of function that takes you from your sensor setup, where the sensors are, how they move, and that sort of thing. It turns it into measurements. And the classification problem is, what is this target? Or put another way, if I have two different targets, can I tell when they're the same or not? One of those targets might well be archived. This is the typical way that people study this. The problem is that if you don't have good control of your sensors, then treating the data as being a function from your sensor configuration space is sort of a problem, because it means you can't even begin to compare the functions. And so what do? Well, over the past few years, topological data analysis has emerged as a possible way to solve this. Instead of looking at the functions, taking you from the sensor configuration to the measurements, instead look at the images of those functions, i.e. the set of values that show up, the raw measurements, and compare them not as functions, which is the traditional sort of thing to do. Instead, compare them as metric spaces. This is perhaps a little bit more tricky to do in practice, although topological data analysis has developed a number of good tools for this purpose. And effectively, the standard topological data analysis pipeline ignores the sensor configurations altogether, just focusing on the shape of the data. Now, the insight I'd like to bring to this particular discussion is that sensor configuration is important. You really do want to know what it is, and it does have an impact in your ability to classify. However, you don't necessarily know all the pieces, but you might be able to distill out a reference space that is somehow a little simpler than the sensor configuration space, and compare on the level of that reference space instead. If the two reference spaces are the same, then you have a basis for doing the standard kind of comparisons that people might want to do. If the reference spaces are different, well, then you probably are dealing with different targets altogether. So mathematically, what we're doing is we're taking the collection from the sensor configuration to the measurements and splitting it up into two separate functions. One function that manages the sensor behavior and one that manages the target itself. We really want to study the second function, the target shape functions. And so what this means is we could ignore the sensor behavior if we could figure out how to do this factorization. Now, the truth is we can't. We don't know what this factorization is, but instead we pull a page from a standard mathematician's toolbox and consider them all, and ask what are the different possibilities, and see how the different possibilities might change. So just to make this very concrete, one of the possible sensor configurations you might have is simply time. You collect a bunch of pulses. You can see on the left, the signal strength varies as a function of time. It's pulsed. You could organize this into a different kind of shape. That is the reference space in the middle there. And finally, you can see the image of the map, which is not necessarily an image as in a picture of the target itself, but rather it has a definite topological feature in it, that being a circle. And so you might say, well, for this particular target, I can identify it by way of saying that there is a definite circle. And the relationship, the blue arrows between these, captures some useful information for classification. And one of the things that I've already found is that for real sonar data collected out in the field, this topological data analysis does actually work. The spaces of echoes that you look at, i.e. the things that you feed into the topological data analysis, the metric spaces, are rather a mess. They look like a knotted ball of string in the middle. That's a projection of this high dimensional space, metric space, down to a lower dimensional space. And you can use the standard tools of topological data analysis like persistence diagrams to classify. If you do this, you get lower misclassification rates than the typical non-topological methods. And so really what I'm trying to understand is, why is this the case? And I think that what I'm going to tell you does provide some good answers. So here's a much simpler sonar target. Again, this is the 3-point target that we had seen on one of the previous slides. The data that we had seen was on the upper left. What happens if instead of traveling around the circle at a nice uniform speed, you do not? Well, it distorts the data in some fashion, so you get the picture on the upper right. If you try to pass it through the usual sonar processing chain, you get a blurred image on the bottom right. But if you look at the space of echoes, the A and B marks, they look very similar. They only really differ by sampling error. And this is why topological data analysis works. So that even though the trajectory has been distorted, the space of echoes is not. So mathematically, what this means is your data that you've collected, your echo data, is a composition of a trajectory function describing how the sensor moved, and some kind of target-dependent function. Ultimately, this composition is what we want to study, and we want to perform our classification on the target function alone, ignoring the trajectory function, because that has nothing to do with the target. So just as a formality, not any such factorization will work. What we're going to want to study are those that are smooth functions and that have a particular kind of factorization, one in which the first map, the trajectory map, the phi, either is a surjective submersion or it is a constant rank map. What this does for us is this gives us some formal control on the structure of the target and on the structure of the data that you're looking at. And what this means is it means you have better control of the degrees of freedom in your data. I'll typically call the target function, the U, a signature, just as a shorthand. And one of the realizations is that if you look at the same target using several different methods, you'll get several different factorizations. The phi map has very different codomains depending on exactly how you're collecting your data. So circular synthetic aperture sonar is on the top. You can see that the phase space, the middle space, is a circle. Whereas for helical collections, you orbit the target with on a helix rather than on a circle. You end up projecting onto a sphere, azimuth and elevation. Same for side scan sonar. And also you can get some stranger ones if you assume a little bit more structure about your target. So if you have two separate targets that are in the scene, the signature will end up winding up on a torus knot. Now, one of the immediate things that comes to mind is that these factorizations are not unique. There's probably many of them for any given collection of data, and of course you don't know which of these is the right one. Which phi map corresponds to your actual trajectory, which U map corresponds to your actual target. There's a possible plethora of these. What I suggest you do is think about each one of these as an object in a particular category, and the morphisms are commutative diagrams that look like this. They're effectively described by the diagonal map going from C to C prime between the phase spaces. These categories, either QuasiP if you're dealing with quasi-periodic factorizations of a single smooth function U, or const U, describing the constant rank factorizations, I think they're actually not too bad as features. And in fact, what I would suggest is that you use the category itself as a feature that you classify on. This effectively removes the trajectory from consideration, and it looks like theoretically just what we want. The signatures that differ only by trajectory or propagation have the same categories, effectively by definition. Signatures that differ by more than that, i.e. different targets, will have different categories possibly. And these categories are functorial themselves. They transform in a nice, reasonable way. Natural transformations make good sense. And in fact, actually, that the categories detect various interesting topological features like torus knot type in some cases. The problem is that it's quite hard to compute these in general and hard to use them for comparison, but I'll give you some leads. Let me first make it clear that this is actually a good feature to use, as opposed to homotopy, which is what the typical TDA things will spit out. The signatures from a rod and a sphere, for instance, are homotopic. Why? Because they're both contractible. They're indistinguishable using traditional topology. Their persistence diagrams will differ somewhat, but the topology will not. Why is this the case? Well, the rod's not perfectly symmetric, whereas a sphere is. So if you look at the data, you can quite see that they're different. And the QuasiP categories, in fact, differ even though they are homotopic. Now, they're actually equivalent categories, so you need to be a little bit careful. We're talking in particular as unusual for category theory. We're actually going to distinguish between isomorphic and equivalent. Isomorphic categories are normally not something you consider. We need to consider them here in classification problems. Now, on the other hand, homotopy can detect things you don't want to see. So in particular, homotopy will detect the direction around the target you've orbited. Of course, you don't really necessarily care what that is. And the homotopy of those two will be different. It detects direction. It's a sign change. On the other hand, the categories are untouched. So that's pretty decent. Now, I mentioned that you can, in some cases, categorize and completely characterize one of these categories. So in particular, if in fact you're dealing with a circular synthetic aperture sonar, start with a circular path around your target. Then in fact QuasiP picks up the cyclic subgroups of the fundamental group. So that's pretty handy, and that does mean that this is actually a new topological feature that's distinct from homotopy. Well, that's pretty neat. How does this work? So here are two targets. One has got a twofold symmetry. It's like two dots or something like that. And the other is a sixfold symmetric target, say a star with 6 points. And I've computed their QuasiP categories for you, or at least the isomorphism classes for them. And you can see that they're, in fact, quite different. And how did I compute them? Oh, because I know how to compute the fundamental group, and I can look at the various factors that show up there. So they're distinguishable, but this still works even if you distort the trajectories. Change the trajectories substantially. They look totally different, but in fact, the categories are unchanged, and of course, that was the whole point. And in fact, if you switch to a different target altogether, you will get, yes, indeed, a different category. That's pretty handy. These categories are equivalent because you can see the object isomorphism classes are the same, but they really are different. So you need, once again, to be careful about the difference between isomorphic categories and equivalent categories. Now, if you say, all right, fine, they're equivalent categories, what does that mean for me? What do I need to do? Well, this means that you can still discriminate the targets by looking at fundamental domains. Because remember, what these objects in the category are telling you is they're telling you about factorizations. And effectively what this phi factorization is doing is it's detecting fundamental domains, sort of in quotes, because they're not really exactly periodic, but they're about as periodic as you're going to get. So you can compare the target on the level of these fundamental domains using traditional methods, and in fact discriminate the targets. So that's pretty handy. And it's especially handy because the trajectory distortions that wreak havoc on traditional methods are just taken out. You don't have to worry about them anymore. And the traditional methods will happily run on them now that they've been effectively compensated for. And now what this means is it means that when you want to do this comparison, you ought to think about effectively equalizing the two targets onto the same domain. Well, this is exactly what this factorization does for you. You can imagine that if you went around the target, orbited around the target in slow time, go around the target, that corresponds in some fashion to look angle. Of course, you don't necessarily know that look angle. But what you could say is you could say two targets have an equivalence, a signature equivalence, if there's a way that you could build a commutative diagram like I've shown on the slide. Now, there are some rather elaborately stated theorems, but effectively what they say is they say that if you have this equivalence, then in fact you get an isomorphism between subcategories. So the presence of an equivalence, which is to say they are in fact the same target, then in fact their categories line up in some particular way, and indeed there's an isomorphism between subcategories. The right way to state this is it involves co-slice categories, which is the reason for all the technicality. Let me show this how this works in practice. So here are two different targets. They're really quite different, but if you zoom in on the fundamental domains, you can see that they're similar. They're not identical, but they're very, very similar. And these matching subcategories are telling you that these are the right places to do your traditional signal processing. Don't do it on the whole thing because it's just too messy and distorted. Zoom in on these separate pieces. Do the traditional comparison there. So this topological method is complementary. Now, what about more elaborate targets? Here are two elaborate targets built up of compositions of different symmetric targets. So they're not actually symmetric at all. The 2-3 torus knot target, for instance, has a twofold symmetric portion and a threefold symmetric portion that fit together. They're superpositioned, or they're superposed. Again, you can see that there's a matching subcategory, and that corresponds to a fundamental domain matchup. And so you can, once again, do a comparison. Of course, you will note the 4-6 and the 2-3 torus knots trace out the same image of points in the torus, but they're not the same knot. They're obviously quite different as knots. They're not isotopic. And that shows up here as an approximate but not good match. Again, approximate match is exactly the sort of thing traditional signal processing does for you. So this quasi-periodic category is only partly signature, where if you have these two targets that are totally different symmetry classes, they actually accidentally have the same category. But again, line up on the fundamental domains and you can see that they're quite different. So the moral of the story is that these topological features are fairly coarse, but once you've got them in hand, then you can apply traditional signal processing and do a much better job of classification. Now, I want to end with a little bit more tricky idea, that being, hey, can I get a metric out of these categories? Well, no, but there's another category that tracks how similar, in fact, tracks all of the equivalences between the categories that are involved. So all of the signature equivalences, they form a category themselves. As you might imagine, the morphisms in this category are much more elaborate diagrams. But in fact, the equivalent subcategory that we mentioned before, that's exactly what this category is. So the size of this category actually appears to be something that works a bit like a metrical quantity. It's not quite a metric for sure. And it appears to be rather hard to compute in practice. But that said, you can see the size of this particular category as a proxy for how similar the targets are. The smaller it is, the less similar the targets are. So the twofold symmetric target, for instance, doesn't look anything like the torus knot targets. And in fact, the CRSE, the category of signature equivalences, is quite different, or the category is quite small because they're quite different. Whereas the two torus knot targets that I'm showing here have a larger category of signature equivalences. So that's pretty handy. Where do we go from here? Well, I think the most obvious thing is that we need to come up with some good ways to compute these signature equivalences and explore what these categories are and see whether we can actually convince them to turn into a metric. Of course, it would be great to extract these categories from data. I suspect that's possible using persistent cohomology. That would be pretty nice. And the linkage there is the fundamental group cyclic subgroups business, which persistent cohomology can give you a bit of a handle on. And in fact, we've got some laboratory data that I'd like to play with, and we'll be doing over the next few months. I hope this was interesting. If it indeed was, feel free to drop me a line. Have a look at the paper that describes this in more detail. And hope you enjoyed it.